how much we know already. So the other day we were working on going through sets, which was the first part of the tutorial. And just to refresh here, a set extends collection. So all of the stuff that collection allows, set will also do. And then for some strange reason, they repeat it all here anyway. So this is already all of the stuff that collection will do. Set doesn't do anything really special. So it already has, a collection already has size, is empty, contains all those other things. So this is exactly what collection is. The key thing about set is that set never contains duplicates. It throws away duplicates. So the example I used this morning, if your set is a bunch of colored things and you've already got a blue thing, another blue thing comes along, you just throw it away. It doesn't fit in the set anymore. You already got one of those. Okay? So it's like sets for kids, right? You get complete set of something, don't need that extra thing, throw it away or sell it or do something else with it. Never belongs inside the set. And as long as you get that in your head, throw away the extra ones, you'll be fine. Okay? So the fact that it doesn't contain duplicates means that one of the things that you can do is you can take anything that you have already that has duplicates in it, you can dump it into something that says set on it, and the thing that you'll get afterwards is something that's guaranteed not to contain any duplicates. So for instance, if you've got a list of people that are in your address book and you happen to have people more than once, presumably if you take that list and dump it into something that says set on it, then all of the duplicates will go away. Only difficulty with that is that you don't know which one is going to be left over, except the answer is it's the first one seen, which is hopefully the one that you want. Keeps the first one, throws away the rest. So he gives some examples of using it. And so in this example, what he does is he has a Java program called find duplicates, and the arguments on the command line are that string. And he says he wants to write a program that lists and print out any duplicate words. And so every time he detects I coming for the second and third time, he reports it, and then he shows all of the distinct words he has left, right? All of the separate words. The way that's done is with this really simple program that just makes a hash set, and there's the fact that it says set on it, means it's not going to contain any duplicates. So you go through all of the command line arguments, and if you see one that's already there, you print out duplicate, otherwise it just gets dumped in. Okay? Now this is a little weirdity here. Add sends back, I think, true or false to say whether or not it was successfully added. So what he's doing there is he's saying if it wasn't successfully added, that means it was already there, so then we'll print out the duplicate. Otherwise, add would just add it. Okay? So I don't like the terseness of that, but that's what it does. Okay? So it's a real simple little program, and the result is, oh, there's a good way to go through and just throw away. So we did a fairly similar thing with one of the examples we had. The other thing he points out about sets is that set, all of the bulk interface stuff, which has those awful names on it, really is useful for doing union and intersection. So there's that set theory idea that you can form unions and intersections of all these things, and so that's the one that we use to find the list of friends that we had in common or the list of friends that were different between us. So all that set theory stuff comes into play there. And so he gives examples of how you do all of that stuff, and it's basically the same as the example that we had, only I tried to do it on a real thing, which was friends, which are more understandable than a bunch of words, which is what he does for his example. Okay. So if you want to see unique and duplicate words, so here he's got that same command line, I came, I saw, I left, and now he wants to show which ones are unique and which ones are duplicate. Then now he keeps two separate hash sets, one that contains unique words, one that contains the duplicate, and he changes his if statement to say, well, we'll try to add it in. If it adds in successfully, then we know that it's unique. If it fails to add in successfully, then we'll turn around and we'll add it into the duplicates thing, because obviously it's a duplicate, and if a duplicate gets seen more than once, we don't care, it just gets thrown away anyway. Okay. Again, there's that terseness. If it were me, I would have put the opening and closing brace on this, and I would have maybe written this in a little longer form, and he's got really awful variable names, A, for these things, but in the long run, that's what it does. Okay. And then he removes all of the any of the duplicates afterwards that were in the uniques, because they've been added once if they were never seen before, so he turns around and removes any of the duplicates from the original uniques to make them disappear, and then you're left with the ones that were totally unique versus the ones that were duplicates. Okay, so these examples don't matter much other than to show you, oh look, anytime you have this sort of problem with set theory, or I need unique things and duplicate things, there's a simple way of doing it. You don't have to go to a lot of trouble to make it work. And the other thing that bugs me about all of these examples is that they always do them on strings. And that means that for string, you automatically get hash code equals compare to. If you're doing this with normal classes that you write, you're probably going to have to make sure that your objects contain equals hash code and compare to, just to make this little game work in some cases. Maybe not all cases, but if you put it in always, then it's pretty much guaranteed to work. Okay, so just remember tree set. That set thing is actually fairly important. And then he moves on to list, which we've used quite a bit, because I keep saying that most of the things that you do nowadays in modern computing, particularly if you're working with GUI stuff and presenting stuff, it's usually lists of small numbers of items that are being moved back and forth in some way, and so it's a natural. The common one there is array list all of the time, so that's one we'd most normally use. And the important thing about lists is that they typically allow this idea of positional access. And so you can see that this thing says that list extends collection, so you get all of the stuff that collection did, and look at all of the stuff that gets added. It's all got to do basically with positional access. Okay, because all of a sudden you're giving it an extra add method that says, oh, I want to put this thing here, or I want to replace this or remove this from this particular location. So lists generally always have positional notation, whereas a regular collection doesn't care. A tree is a collection, and we don't really care what position things have within the tree. So it's only list and array list that care about positions.
Sorry, back to your set. You say they can't contain duplicates. So does that mean, like, say for friends, that it checks the friends equals to make sure that it's already in the list, or?
It uses compare to. The other thing about tree set in particular is that it uses compare to typically.
Okay.
So equals is by whether it's not less nor greater than.
0, then it's equal.
Right.
Gotcha, right.
And it throws away subsequent ones. Right? I've already got this baseball card. I don't need another one like it, so that one can be sold or thrown away. So we've seen index of for list is one that we've used fairly extensively. And notice that index of is this little misleading thing here, because you look at it and it just seems like you give it this weird object, and now we know that's a little more complicated than it seems to be. Why is there a last index of, by the way? Why would you use last index of? If there's duplicates. So if you call first index of and last index of, and they don't use this, give you the same position, then you've got more than one of those things in there someplace, because index of will only pick out the first one. How about list iterator? Lists have a list iterator. What makes a list iterator different from a regular iterator? Hint, look at this one. You can start at a certain position in a list. The other thing about list iterators is that they allow you to move backwards. So you can only move forwards, but there's actually a has previous, so you can go backwards in the list, which is sometimes fairly useful. And the other thing it has is that you can get a sub-list. You can look at just a portion of the list if you want. There's an option to do that. Vector was this old beast that was in the original versions of Java. We don't care about it anymore, so you can skip that. Add all will dump stuff from one list into another list, so that's a really convenient thing because quite often you end up adding more things to a list. And so in general, all of the stuff is transposable. You can copy things from one thing of a collection into another thing. Making copies is really easy and really efficient. Okay, so here's an example of making a copy of an existing list and then dumping in some extra stuff. So you've got basically the sum of both lists and left the original alone. Okay. Lists have positional notation, right? So there's the, get something. So what he did here was he wrote a swap routine. So you give it a list of some type of thing and you give it the two positions that you want to swap, and what it does is it grabs the first one into a temp, sets the second one, sets one and then puts the other one back. So a standard swap routine. The joy of this is that now this becomes totally generic and you can use it to swap anything on a list, and that code is actually, there's a collections.swap that does exactly that. So you don't even have to write your own. You can just call collections.swap to swap things on a list. Okay. How about shuffling things on a list? How's that for a terse piece of code? So if I say I've got a list of 20 things and I want them shuffled in a different order, what's the best way to shuffle them? Just off the top of your head. Swap them randomly, but doing what? Where do you start? What's going to make it random to get all of them to a different position? People get really weirded out sometimes when they write this, but it's not as difficult as it seems. Yeah, which is sort of confusing. But if you're not looking at this code, if you're just looking in general, if I say, how do I get everybody in this room to change positions? What do I do with them?
Put them somewhere else, switch them with anyone else.
Switch them with some other random person, and then what do I do?
Go to the next person.
Go to the next person and
Do the same thing.
same game all over again. So randomizing a bunch of people in a room is really easy. The trick is all that you do is you basically go to each one and say, hey, I'll offer you the opportunity to change positions. They can generate a random number, they can move to some other position, the random number may put them back in the same position, that's fine, they've had their opportunity to move. So really randomizing a list just means going through every single person and giving the opportunity to switch. Okay, so that looks like what he's doing here, because he's got the random number generator and there's the new position based on the maximum size of the list. The question is, why is he going backwards? Good answer. Because he's an idiot. I've looked at this example a whole bunch of times, and as far as I can tell, there's no reason at all to go backwards. You might as well just as easily go forwards to the list and offer people an opportunity to switch. The backwards is doing nothing for you other than complicating your life. So even people who write example code and write stuff that's just sort of weird. Okay? And so this gets back to my point about I'm always going to try to write for loops going in a forward direction, counting by one, and life is generally easy, and that usually works. And there's not much reason to do this other than to decide to complicate your life, because now you've got to worry about where the thing is that you're swapping. So you've got I involved in the calculation of the position in a really weird way. Okay. So collections.shuffle basically plays the same sort of game. He points here, he mentions arrays as list, and we've used arrays as list as a way of saying, oh look, here the definition for when you start up a Java program, it's been around long enough that when you start up your program, you get an array of all of the arguments. That's never going to change. They're never going to retrofit that to be list. So if you want those arguments in the list, the first thing that you do is you use arrays as list to say, I'm going to treat that array as a list, and now you can shuffle it, okay, and do all of the regular list stuff with it. So there's arrays as list used as a conversion routine when somebody gives you an array and you just rather not deal with an array anymore. There's our list iterator, the interface for list iterator. And list iterator not only has next and next, but the additions here are has previous and previous. Okay? And so you can work your way backwards through a list. By the way, well, actually, we'll get to that, so I won't talk about it now. You can find the next and previous index to see where you're about to go. And notice that this is an interface, but it says that remove is optional. Isn't that weird? You think of interfaces as being, oh, you have to do this because this is the standard. And now all of a sudden you've got somebody saying, well, I know it was standard, but it's optional. Okay? So this is, I always call this the 12-year-old approach to interfaces, which is like, well, you said I had to write it, so I'll put it in here, but if you go look at the routine, it's got nothing in it, but hey, I wrote it. Okay? I did what you said to do, but it has no chance of working, but hey, this was all you said is I had to put the name in. Okay? So that's why it's optional. Sometimes you write it and don't. It's there for most list things. Why is remove important? Where is the case where remove is really efficient? That means remove the current one. Linked list, why? What's the iterator doing that's different for a linked list compared to an array list? So if I've got an iterator through an array list and I'm at position 5 and I say, oh, we just looked at this one, remove it, I don't need it anymore. What does it have to do? All the ones after now have to shuffle in order to get rid of position 5. If I've got a linked list and I'm standing at position 5 and somebody says remove 5, what do? This is a doubly linked list, by the way. So if you're standing at position 5 and somebody says remove 5, you take one step backwards to get to 4, link 4 to 6, stand over top of what's now 6, which is now 5, and keep going. Okay? So if you want to remove a whole bunch of things from a very long list, it's actually easier if you've got an array list to copy the thing into linked list, make your linked list, because that's efficient because it's going to dump on the tail pointer to make the list, and then go through and run remove and filter out all of the things that you don't want, and then put it back into an array list. On a long list, that's going to be faster than trying remove from an array list. Okay? And so if you know a lot about how these things are working internally, you can write somewhat more efficient code by going, oh, I know this is a bad thing to do, but just let me copy it elsewhere temporarily, put it back, off we go. Doesn't matter for short lists. If it were 100, 1,000, maybe 10,000, who cares? But if you get really, really long lists, then there's a benefit to starting to worry about the performance of these things. He says, here's the standard idiom for working backwards through a list. Oh my God. So here's the first weirdity of using list iterators has previous. You would think I would just be able to make a list iterator, say, I'm starting at the back, so has previous should give me the last one off the list. It doesn't. What you have to do is you have to set the list iterator to go to the end in order to start using has previous. Okay? So list iterator takes that argument because normally if you're starting at the back, you have to get to the back first and then work your way through. Okay? So that's the weirdity about putting the size in to start it at the end. Okay? What's missing from the for loop? The increment. Why is the increment missing from the for loop? because you have to put the previous down here so that you can capture the value. So the previous is actually going to cause the advance to happen backwards. Okay? And so this is one of these cases where I'm looking and going, well, this is really a hybrid, because it's not a complete for loop, because it's missing this thing, and it's not really a while loop, but it's being used like a while loop, because typically in a while loop you have to change the condition in order to get the loop to stop. Someplace inside the loop you have to change the condition, right? And so that's what's happening here. So it's neither a for loop nor a while loop. It's this weird combination of both. And so this guy uses it a lot and tries to convince you that this is the standard way of writing it. If it were me, I would write this as a while loop, because it just makes more sense to go, you know, I'll start out here, I'll start at the end, while has previous, oh, I'm going to go get the next one, get back, and follow the while loop pattern, because that's another standard pattern. So I'm saying either use a for loop as a for loop or a while loop as a while loop, but don't try to make the for loop pretend to be a while loop when it's not. Okay, which is what that thing is doing. Okay, there's another weirdity about previous and next, and he tries to draw a real some sort of weird diagram in here to explain it, and I can explain it a lot simpler. Okay, if I'm moving through a list of things, and I'm moving through forwards, and I'm saying, say your name, say your name, say your name, and now I decide to move backwards. What happens at this point? If I say I'm going to reverse direction, now say your name, whose name gets said? No. Because I'm still standing at this one. Okay? So it's an oddity of, if I say your name, I've actually sort of advanced to sort of between them. And the next one that I'm going to say is this name, and the next one I'm going to say is now going to be this name. And then I've actually sort of come to here, but I haven't done this one yet. So if I turn around in reverse direction and say your name, the one I'm standing over is the one that I was just at. Okay? And so the weirdity about reversing direction is anytime you do it, it seems sort of counterintuitive, but you always got to take 2 steps back, because the first one is the person you just saw. Got that? Or be careful about reversing direction, because it might not do exactly what you expect. There's your hint for that one. So that's all he's basically always trying to say there. In all sorts of weird ways. Okay. List also has set and add, so you can change things as you go. So here he's trying to replace things. He's trying to write this routine that just says, here, replace things. I'll give you a list. Here's the thing I'm looking for, and here's what I want you to change it to. Okay? There's his weird loop that doesn't do the increment because it's inside. How about that wonderful line right there? See that little question mark there? Do you remember the question mark operator from your C class? That's what's officially known as the ternary operator, which is a short way of writing an if-then-else. Okay? So this is the if part, that's the then part, and that's the else part, all written on one line. Okay? I grew up as a C guy. I wrote a lot of C code. I read a whole bunch more C code. Every time I see this little question mark operator, I twitch. Because I look at it and I go, what? And it just always makes me stop and have to think, and I just wish people would stop using it and write a normal if-then-else. Because it's this terseness thing. It just becomes so terse that it doesn't make things obvious anymore. Okay? Why is he checking for null? there's a reason here why he's got to do this check for null, and it relates to that piece there.
If we're at the end of the list?
What's that?
If we're at the end of the list?
No. Remember, lists can have nulls in them.
Doesn't want to add a null value.
So if lists have nulls in them, then you can't just call something dot equals something. So if you had a student in the list, then it would be student equals whoever the next student is on the list, that's fine. If there were all students on the list, that would work. But if you allow null values in the list, you can't guarantee that you actually have something that will allow you to call equals. And so what this thing says, well, we'll check to see whether or not the thing on the list is null. If it's not null, then the answer is, we'll just go on to the next one. But if it is null, we can check and see whether or not there's a match. Okay? So it's a specific weirdity that gets introduced because you're allowed to have null things on the list. And so the rule in modern Java has become try not to put null things on lists and try not to return null things, because anytime you do something like send back a null, you're forcing whoever gets the null to have to check to have, do I have one or don't I? And so giving a null back automatically means you have to write an if-else in your code someplace. Where did we just see that? In alternate comparator. The fact that alternate comparator in the last lab could be null meant that anytime you went to go use it, you now had to check to go, oh, well, if it's there, I can use it, but if it's not there, I guess I should use this other one. Okay? So the fact that it could be null meant that you always had to write an if and else. Okay? And that's a problem. And so in the lab solution, I'll show you a way to fix that, which is to basically get rid of the null. Okay? So the point here is that lists can contain nulls. You're better off not to do it. He's trying to write a generic thing that will work for all lists, including lists that do a bad thing and have nulls in them, because there is actually a collections.replace that will do this. Okay? Notice, though, that the bottom line of thing here is that equals is used to say whether or not that one matched the other one. And that's traditionally true, which is the reason why we've spent so much time on getting equals to work. Range view operations, you can take sublists of things, and there's a few sorts of idioms he gives to play with sublists of things, and I'm not really all that concerned about it because it doesn't really get used all that much. He has some card sorting stuff there. And here's a more or less complete set of things that you can do with lists, the algorithms. We've seen collections.sort, we've seen collections.reverse, there's a collections.shuffle I think we've used to randomize a list. There's a few others. There's collections.swap, which you've just seen the code for, so that you can change the positions of two things on a list. There's a replace all, which you've seen the code for. Binary search only works if the lists happen to be in order. So there's a few other little utility routines in the collections library that are sort of interesting. Okay, Q we looked at. Q has basically add and remove. The offer and poll are ways of doing things with the list to see whether or not you throw an exception. So if you use just add and remove an element, then you have to check the size of things before you go about trying to get things off the list, versus if you want to use special values to check and ask the question, have it return true or false or whatever, there's a separate set of those. But you can see, usually you stick with either this column or that column, just to be consistent in how you do it. And we never had things throwing exceptions because we always checked to see whether or not they were there first. Okay. So important thing about queue is it just takes them basically in order. And the other important thing about queues was what? What was special about queues that made them?
On both ends.
There's always the notion of two people playing the game. Okay, so there's always the notion of somebody trying to fill things at the back end and somebody trying to clear them off the front end to get rid of them. And you can immediately see that from the example that he's showing you, because notice that he makes use of a thread here to try to get the independent thing throwing things away or doing something with the queue. So he's got somebody who's adding things on the front, and then he's got a thread playing the game of removing something and then sleeping for a while and then waiting. So there's the sense of he's trying to get something independent in there to do the removal compared to the addition. Okay? So almost always the case with queues that you see them used in sort of more operating systems type things, or getting stuff from a network where things are coming in and they're coming in too fast, and so you build up a queue while you're trying to process them. That's typically where it gets used. Okay? And we saw a priority queue as being the one that we used for our lab, so it's a special kind of queue, and you know that priority queue requires the compare to in order to work. Now, the one that we haven't used so far is this thing that's called a deck, and a deck is basically a double-ended queue, and a double-ended queue means that it can either behave basically like a stack or a queue. Okay, so it's got the option to add or remove things from either the front or the end. It's a doubly linked list, so it's generally easy to remove things from the front or end. It's pretty efficient. Doubly linked list with a tail pointer, you can do either or. And so depending on your choice of operations, if you always add and remove on the front, or always add and remove from the end, then you get a stack. But if you add and one at the end and remove from the front, you get a queue. Okay? Is it a good thing? It's a good thing if you've written this thing, because then you get a twofer deal. It's a little bit of a bad thing because people who look at it now have to ask themselves the question, is somebody using it as a stack or a queue? Right? And it's not obvious unless you actually look at some of the operations. Are they always adding or removing from the front? Oh, it's a stack. Oh, okay, are they adding at the front and at the back and then getting it from the end, and you can do it from either end, and so it's just a mess. And so much as this is a neat thing, my recommendation is to stick with queue and stack, which are also in the libraries, because they tell people more exactly right away what your intentions are with the type of problem that you're trying to do. Okay? So stacks are typically used for problems of how do I get back to where I was. Queues are usually used for problems of too many things are coming in for me to process. Okay? And so if people know that up front, it just makes their lives a little easier. Okay? And so deck, you can peel things off at either end, peel or add things off at either end. So it's a sort of a general purpose facility. And now we get to map. Map is the one that doesn't play well with others because it takes two things. And so notice it doesn't even use add. It uses put to try to emphasize that it's just not the same. Okay? So this is the one that's difficult to go between the others because it's always sitting out by itself by virtue of the fact that it takes two things all of the time. It takes a key and a value, and this is the only one that we've seen that does that. Remember, key means unique. So if you have two things that share the same key, they've got to be unique on purpose. Okay? The rule for maps, the easiest thing I can think of is to say they behave just like arrays. If you think of them as just being an efficient squashed in size array, then think of the key as being, position 5 in the array, and there's the value I want in position 5, because the key just basically becomes a number, regardless of what this thing says it looks like. Okay, so if I ask you the question, well, okay, if I put something else in position 5, what happens to it? Well, it behaves like an array, it just gets replaced. Okay, that's all there is to it. So maps are basically a form of an array. And just like with an array, what you're trying to do is you're trying to associate two things together that didn't necessarily belong together to start with. So an array, you're saying, oh, I think position 3 should hold Fred. That's an association of a number with Fred, right? So you're trying to pair two things together that didn't necessarily belong together. Okay, so the same thing here, you're trying to pair a string, for instance, with a particular value. It's still the same idea. Pair a unique thing with something else. Strings work well for keys because it's easy to change a string into some magic number. Okay, and so it's really just, if you see string in there, it's just the same as using a number, basically. The only thing that's special here is that key, whatever goes in the key, you know that hash code and equals are going to be called. And so you have to be really careful if you're using anything but string here, meaning you're using your own object as the key, chances are pretty good that you're going to need to override hash code and equals. So it's just generally a better idea to always do it in those low-level things that you make, and then it's just always there for use in a hash table any way it wants to be used. Okay. You can remove things, you can check to see if the key is there or if the value is there, so nothing particularly fancy. The other thing that you get back from this thing is this idea of an entry which contains both the key and the value. Okay, because you paired things up to begin with, and so if you ask for the pair of things back, you can then get both things out of them. And so it then has basically 3 different iterators, because you can either ask for just the keys, just the values, or the pairs of things together. Okay, so that's what those different views are, is the 3 different things that you can get back together. Hash table was the old one. Don't need to worry about it anymore. It's gone. Okay, we had this this code that counted to see whether or not how many times something had appeared. Right? Here's his version of the thing. He makes a table with strings and integers. And so if you look, what he's got is this command line that has that argument, which there's a bunch of repeating words in there. And so what he wants to know is the word count for all of the words. Is what he's getting out of it. Okay? How does he do that? He goes through, he makes a hash map. The hash map has got strings versus count, right? Because there's the string versus the count. Okay? String is useful here because it has hash code and equals built in, so it works fine for the key. He goes through all of the command line arguments. He tries to get out the existing frequency. What's that weirdity doing? Oh, look, there's our friend the ternary operator in there again. Why is that weirdness in there? Yeah, if it's never been, when you try to retrieve it, if it's never been seen before, this integer is going to end up with a null in it, right? It's going to get translated into a null. So he says, if it's never been seen before, then we'll give 1 to it. Otherwise, we'll take the existing frequency, add 1 to it, and store that back in with the same key. Okay? And so, like I said, I'm not a big fan of the ternary operator just because it makes things too terse. I would have written this as a nice if then else like we did in our sample code because it just makes it way more obvious. Okay? Well, now the next question is, what if I want all those words in alphabetical order? And the answer is, oh, well, that's really easy. What you do here is you take this same code and instead of hash map here, you replace this with tree map. And a tree, you know, will keep things in order based on compare to of the keys, which are done by strings, and lo and behold, you get things in sorted order. Okay? So again, once you start to use these things, a lot of the things that you would expect to be difficult can actually be really easy. Okay? A point about copying maps, it's possible to copy from one hash table to another, but they have to have the same key and value in order for it to work. If they're any different, it just can't work at all. And you can't generally copy them to things that aren't another hash map without going to some trouble. And we'll skip that little section because it's sort of unimportant, and the anagram section, just because it's relatively unimportant. We've seen that you have to write compare to. And so here he's saying in his object ordering session, he starts out and he says, oh, you can sort a list. Why didn't he just say a list or something there rather than L, which looks like a 1? Oh well. We know that if you want to call collections.sort, that the thing that's on the list